coming here to listen to the MS exam of Conor Wallace. Conor had been in our research lab when he was even end of his junior year. He's spent 3 years in the lab and has contributed immensely in every which way to the mentoring a lot of kids and a lot of younger students and collaborating with other students at his level, and already accumulated a excellent track record. And I'm so glad that he's already secured a very good job already in this COVID-19 era, which is getting worse and worse every day. I'd like to thank Dr. Richardson and Dr. Benavides for accepting to be on his committee. I would like to now give the screen to Conor to present his master's work.
Thank you, Professor. Let me go ahead and share my screen with you guys. All right, can everyone see just fine?
Yeah, we can.
Okay, perfect.
Yes.
All right, well, welcome everybody. Thank you for being here. I thank you for coming to my defense, where I'll be defending my master's thesis for my research on fault diagnosis for mobile robots under dislocated actuator faults. So just a little bit of background. Fault diagnostics is a category of control engineering that can be broadly diagnosed into two different approaches. It is fault pattern recognition via sensor readings, and then analyzing residual error between recorded sensor readings and the expected values. So this research tries to take advantage of both of these approaches and combine it into one novel fault-tolerant control method for a UGV with dislocated actuator faults. So the testbed that I'm using is a custom-built UGV built in the Autonomous Controls Engineering Lab, mainly by Dr. Benavides, and with the help of one of our ex-master students, Abhijit Majumdar. It is a four-wheeled UGV, and the fault scenario that I am studying is a dislocated suspension fault initially. So basically I have three fault conditions. I have a healthy suspension, I have a left dislocated suspension, and a right dislocated suspension. So first, I wanted to get an idea of the natural drift perturbed by each one of the fault conditions. And so what I did was I would drive the UGV straight for 270 time steps, and then record trajectory data, so the three states of the system, X, Y, and theta, and then record that to a data set. And I did this 20 times for each fault classifications, which ended up with a fault data set X, which was in 60 runs by 270 time steps by 3 states per time step. So the literature in fault-tolerant control can be broadly summed up in 4 different topics. The most simplistic topic would be just to use the expert knowledge of your system to set a hard threshold of performance drops in order to detect and accommodate a fault. A more intrinsic way of doing things would be to create fuzzy rule sets to determine regions of uncertainty for fault behaviors and adapting a control law according to the fuzzy inferencing. Another more novel version would be to combine the learning capabilities of deep neural networks and identify faults and adapt control laws using fuzzy inferencing. And then we actually have a paper published in this domain that which is the paper that Jim Sheedy was talking about that we presented in Alaska last year. So we have some expert knowledge in that domain. And then the last, most complicated version is using deep learning for end-to-end fault-tolerant control by both learning the fault patterns and also learning the necessary control to accommodate the fault. So what I'm trying to do in my thesis is A, create an unsupervised learning scheme to identify fault patterns in an unlabeled data set. The idea for that is that I want to be able to identify new faults as they come in, starting off with a pre-existing unlabeled data set, and then identifying new faults as they are put into the data set. Next, I want to fit a noise distribution to the fault data for each of the different clusters that were identified. Then I want to optimize a set of control laws to accommodate each fault identified in the data. And then finally, I need to develop a real-time LSTM-based fault diagnosis algorithm in order to determine the optimal control law for each detected fault. So like I said, the testbed that I'm using is a four-wheeled UGV, and this is classically modeled using the bicycle model. It is a mathematical model that is used to simulate the UGV as best as possible, where you have three differential equations. You have x, y, and theta, which represent the states of the system, where x and y are the center of gravity of the UGV, and theta is the yaw angle. It's the heading of the UGV. And then this model is from Peter Cork's vision-based control MATLAB textbook. So the control law that I'm using is a proportional derivative integral PID control. PID control is based off of an error. You're trying to basically use gain values, basically weights, to model a control input based off of error that you're measuring from the system. So since I have two controls, I have, like as you can see here, I have velocity, and then this is my steering angle. So I have two controls that I can use to control the UGV. And then I need two PID control laws for that. So for the forward velocity, I'm using the Euclidean distance error. And so this is the Euclidean distance between the current target coordinate, so xd and yd, and then the current coordinate of the UGV, so xft and yft. And so in order to actually calculate the input v of t, you compute the proportional integral and then derivative. And I should mention that this is a discrete time PID control law, because I'm working with a discretized system for more realistic results. And then I have the same thing for the steering control, where it is the difference between the current heading of the UGV and the error from where the current UGV is to where the target coordinate is. So basically the difference between these two headings. And then this phi, this is just to cap the heading error between the bounds of negative pi over 2 to pi over 2, to make sure that it's actually steering the way that it's supposed to be. And then the same PID control here. And so what I do is I take all 6 of these PID gain values and I place them in a control gain vector k. And then this is going to be my optimization vector later on when I get to the control optimization. So the base experiment that I'm using for this thesis is a path planning experiment. Basically what I'm doing is I'm using the A-star path planning algorithm to take in a cost map, as seen in this figure, where when you look at the white space, this is traversable area, and then the black space is some kind of obstacle. And this is a really simplistic example, but the idea with this is just to give like a real world scenario of what the UGV might encounter and what it might need to optimize for. So basically what I do is I get all of the points along this path, and then I interpolate in between those points for further resolution, thus resulting in the matrix B, which is 940 trajectory points. These are the same x, y, and theta points. And so what's good about this experiment is it allows me to subject the UGV in simulation to one of 3 health conditions at random with realistic constraints. It also allows me to record several data features such as trajectory data, UGV control inputs. It's very good for experimenting with different features that I could record. So the total fault diagnosis, the fault tolerant control system diagram is seen here. Basically, I have it split into 2 parts. I have an offline process and I have an online process. The offline process pretty much takes care of all of the data analytics. Basically, it starts with a database, which is at first set to be this initial drift data set that I recorded. We use spectral clustering to actually identify fault patterns in the data, and then nonlinear least squares regression to fit a noise distribution to the clustered data, and then use genetic algorithms to actually optimize a set of PID control laws for each of the clusters. And then this is also where the training of the LSTM classifier takes place. And then the online process, you have the actual UGV dynamics, and then you have the LSTM that is making predictions on the health condition of the UGV, and then subsequently is making decisions on the optimal control law given the predicted fault. And then the thing that's interesting about this is that it's a cyclical cycle. And basically what I mean by that is that every time that you run this online process, it's recording the same vector of data, and it is storing it back into the database. And the idea is that you use this same offline process to identify the newly recorded data so that you can pick up any new faults that have occurred. So spectral clustering was originally designed for image segmentation. It's based off of a method that uses graph Laplacians to cluster an affinity or a similarity measurement matrix of the given data set instead of just purely from the location. It is able to work with non-convex data that traditional clustering techniques such as k-nearest neighbors would not be able to handle very well. And then as such, it's an optimal technique for this application where the UGV trajectory is very likely not to be convex. The first thing I needed to do before I actually run the spectral clustering, though, is to convert the time series drift trials into more manageable segments of data for the clustering to handle. The thing with clustering, with most clustering methods, is that separability between data is key. So if I go back to the actual data set, you'll see that no matter what, they all start from 0, so they're all connecting at some point. And most clustering methods are going to have serious problem trying to actually tell the difference between any of these. And so typically what ends up happening is you just have these vertical partitions where it thinks that, you know, these are just vertically separable because it's the best thing it can do. So in order to address that, what I did was I converted the time series trials into a set of statistical features of each of the runs. So the considered features were the largest magnitude of error from the line that it was trying to follow, the mean of the run, the variance of the run, the kurtosis, and the skewness. And basically what I wanted to do was to plot each of them against each other and determine which ones presented the most optimal, the most separable data set. And so what I ended up discovering was that the optimal set was the largest magnitude of error, the kurtosis, and the skewness. And so what ends up happening is you convert this original drift data set, which is in 60 by 270 by 3, to this statistic feature data set, which is in 60 by 3. So one of the other known problems of clustering techniques is the fact that you need to know the number of clusters to separate your data ahead of time, which there's plenty of work in the literature to discuss how to optimize that number, because in my case, I'm assuming that I don't know the number of faults. Therefore, I don't know the number of clusters that the data needs to be clustered into. So what we ended up doing was we took a series of internal validation methods and created a consensus of the likelihood that the current number of clusters is correct. Basically, we just iterated from one cluster to n clusters, and then took all of the internal validation methods to try to get a consensus. And so using this approach, we created a ranked voting system, which was used to analytically assess the optimality of a given number of clusters. This was done by iterating, like I said, over a given range of clusters, and then summing the votes from each of the internal validation methods and for each of the number of clusters that we were testing, and then save this data to a vector v, where the indices of the vector v are the number of clusters that we recorded. Then confidence vector c is computed by feeding v through a softmax activation function, where each number of votes is then transformed into a probability of confidence. And the idea here is that basically we accept an optimal number of clusters if the probability confidence is greater than 50%. So here you can see, this is the 3D plot of the 3 statistic features that we computed. This is the healthy statistics, this is the right statistics, and these are the left statistics. And as you can see, we have a cluster accuracy of 100%, and it determined the number of clusters to be 3, and it had a confidence of 69.87%. So in order to transfer the original time series data, we basically mapped the statistic feature set back to the original time series data set, and then labeled that set accordingly. So you can say this is the original data set, and then this is now the clustered data set, and as you can see, they're identical. So one more thing that we wanted to do, because the idea with this is that it's able to pick up on new faults as they enter the data set, was I recorded 20 more trials of a new fault, and the fault being that I dislocated the front right tire of the UGV, which caused the UGV to severely drift towards the direction of the dislocated tire. And basically, what I did was I would feed in each one of the trials one by one, and then let the clustering algorithm determine what the new number of clusters was. And given only 3 new trials, it was able to determine with a confidence of 71.21% that the correct number of clusters was 4, which is the correct number. Now, 3 samples versus 20 samples for each of the other classifications is obviously a very unbalanced data set, so it's good that it performs so well given the unbalanced data set. However, it would be better if we could get it to identify the very first run. And this is something I'll talk about a little bit more about in my future work, something that we could use to address this. However, so now we have a clustered data set into new identified faults. And so what I want to do now is fit a noise function to each one of the trial runs, each one of the clustered trial runs. And the idea with this is that I want to be able to generate a generative model where I can just select at random a new noise function to simulate a fault, so that I'm not just taking the original data. I want it to be random and generative. So what I did was I created this noise function g of t, which is equal to gamma n, which is just, it's a constant steering angle, and plus a white noise term. So this is a Gaussian random variable with 0 mean and 0.001 variance. And so basically what I did was I adapted my bicycle model, and I add the noise function to the steering angle input of time t. And basically what this simulates is the UGV being pulled into the direction of the dislocated suspension at every instance, so that the optimal control law will have to combat this. So given these new dynamics, I need a nonlinear least squares optimization objective, and this is simply just the y trajectory data of each of an individual drift trial run minus the output of this dynamic equation given this gamma n. And basically what I'm trying to do is I'm trying to minimize the difference between these two output vectors. And this is subject to the constraints that this gamma n is when the bounds of the actual UGV, which is plus or minus 0.785, i.e. the bounds of which it can actually turn. And so in order to actually optimize this objective function, I'm using an interior point method. I'm using the subspace trust region interior reflective optimization algorithm. It's an algorithm that is, it's mainly meant for nonlinear function optimization, and it works with both constrained and non-constrained optimization problems. And so here you can see at each iteration what it's trying to do. It's trying to find the actual gamma n such that it fits this noise, this drift distribution exactly with the recorded data up until some amount of error. And so that was actually done for each one of the trial runs in the drift data set. And so what I did from there was I separated them just how they were in the clustered drift data set, and then I calculated the mean and the variance of each set, and then I created a Gaussian random distribution of each one of them, which you can see in this figure right here. And as you can see, they are completely separable. And the idea with this, once again, is that this is a generative model, so I will be able to, in simulation, if I decide that I want to run a healthy simulation, I can pull a new random noise drift function from this distribution, and same thing with the other faults that are optimized for. So now that I have that and I can realistically simulate the system, I need to optimize a set of PID control laws. And so like I said, I'm doing that with a genetic algorithm. So genetic algorithms are a gradient-free optimization method. The reason I needed a gradient-free optimization method is if you try to backpropagate all 940 differential equations to get a gradient for gamma or for your PID control, it's too cumbersome. It won't work, and so I didn't even try that. What I did try was I tried just calculating one point to see if it was convex, to see if I could do any kind of gradient manipulation with it. And even locally around just one time step, it is very much not a convex optimization function. So gradient algorithms were completely out. So gradient-free algorithms work particularly well with this type of problem, and so the genetic algorithm was chosen as the method of choice. So what a genetic algorithm is it is based off of Charles Darwin's theory of the survival of the fittest. The idea is that you have a population, an initial population of possible solutions, and these the idea is that you calculate the fitness, so like how well they solve your problem. You calculate the fitness for each one of the solutions in your population, and then you only select the top n fittest members, and then you perform crossover so that you can actually generate a new population. And then if by chance, you will also mutate your new generation to create new and then manipulate your search space. So this is done typically until you hit some convergence criteria, but this is done for an entire evolution. And so basically what I'm trying to do is I'm trying to minimize this objective, and this objective is the L2 norm between the A star optimal path at time t and the computed trajectory state of the adjusted dynamics given the new noise function, and this is also subject to this constraint, which I'll talk about in a second. But like I said, this K is the chromosome that's based off of. Each one of these is a different solution to the population. So like I said, the mutation function is perhaps the main tool used for manipulating a search space using genetic algorithms. Basically, the idea is that you have a mutation rate, and this is basically just a hard threshold from the range of 0 to 1, for which each individual gene of your chromosome needs to surpass in order to actually generate a new value. So basically, each one of these indices in my vector k has some probability associated with it, and it needs to surpass this mutation rate at each generation. And if it does surpass it, then it will produce a new gene for this member. And like I said, each one of these are subject to this mutation rate. So the idea is that not an entire individual will be mutated, but possibly just its individual genes of the solution will be mutated. And the way that I actually manipulate the search space is using applying each of these genes to a Gaussian distribution. And this Gaussian distribution, its mean is centered around the current best solution, and its variance also is according to this mutation rate. So basically, it starts at 3 standard deviations to get a good search space, and then as the evolution continues, the search space continually gets smaller and smaller and smaller until it eventually converges on an optimal solution. So it's fairly similar to the same trust region search method as seen with the noise function optimization. So here I have plotted the actual objective function surface. So the idea, I have 6 optimization variables, and obviously I can't plot 6 dimensions, so I compress those features into just 2 features using PCA, which I'll talk about here in a minute, and then computed the fitness score for each one of them and then plotted them in this plot. And basically what you can see is that what I'm looking for are minimums, because I'm trying to find the smallest, I'm trying to minimize my objective function. And what you can see is that this is a highly stochastic optimization objective function surface. And so as such, it requires a fairly large mutation rate for maximum search space. It also requires a large number of generations to converge on a desirable solution. The other thing is that since it is so stochastic, an optimal convergence is not necessarily feasible, so suboptimal solutions may be acceptable. So the actual evolution process, I used 100 individuals per population, and like I said, the individuals were the K gain vector. So there were 100 of those per population, and then I evolved the generations. I evolved the population for 100 generations. My convergence criteria, since it is so stochastic, and also we don't really know exactly what the convergence should be, it's just to exhaust all generations. So one problem that I encountered when developing this, and so I should mention that this was a custom built GA class. This wasn't from MATLAB. One thing that I encountered is the fact that it needed to, for each fitness calculation for each of the individuals in the population, it needed to calculate 940 separate differential equations, and it needed to do that 100 times per generation. And so basically what I was seeing was that I was getting a fitness per generation runtime of approximately 120 seconds, which if you do that for 100 generations will exponentially increase your runtime to something to the order of 7 hours. And so what I did was I parallelized this fitness function by using multiprocessing and taking advantage of multi-CPU technology. And after parallelization, you can see that the fitness per generation runtime is reduced to 1.2 seconds. So this GA evolution, which originally took to the extent of 7 hours, is reduced to just 20 minutes. And then as you can see, here are the actual, so this is the actual A-star path that I was given. And then this is the healthy UGV, the left fault UGV, and the right fault UGV. These are the actual paths that it's able to run with its optimal solution. And then these are the convergence plots. So now that I have an optimal set of control laws to pick from, I need to have a way of actually deciding what the current fault is in the UGV. And so what I used the LSTM neural network. And LSTM neural networks are a subset of recurrent neural networks, which are basically a way to analyze time series data. The idea is that you want to analyze the evolution from one time step to the next time step through a series of time steps, and we call that the window size. And so one thing I should mention is that the sampling time of the UGV control for this study is 100 milliseconds or 10 hertz. So basically, every second it has 10 updates, which means that every second we have 10 new feature vectors that we're computing. And the idea is that I want my window size to be as small as possible so that I can get an update as quickly as possible. So I reduced the window size to just 10 time steps. And I obviously experimented with the window size. If you increase it, it increases your accuracy at the cost of not being able to predict in the time frame that you're allotted. And also if you increase it too much, you may just lose information. You might not be able to predict that far into the future. So the window size that I used was 10 time steps. So the LSTM model that I actually end up using is a deep neural network. So it has two CUDA LSTM layers. I should mention this was developed under TensorFlow using Keras. So CUDA LSTM layers are NVIDIA optimized to run on your GPU in parallel. And in studies that I've seen, they have reported that the runtime is sped up by upwards of 300%. So CUDA LSTM layers were optimal for this application. As well as that, I'm using two dropout layers with a dropout probability of p. The idea with dropout is I'm trying to reduce overfitting by randomly dropping information from one neuron to the next neuron. Speaking of which, I used 128 neurons per CUDA LSTM layer. And then finally, for the output layer, I used a densely connected layer with F neurons, and F is the number of faults that I've recorded. And then I use the softmax activation function for that, which once again gives you a confidence interval as your output. So before I actually get to training, I needed to create a new data set, because the idea with the with the LSTM fault diagnostic prediction model is that I need to predict what the fault is under closed loop control, and so I needed to record a new data set, and I wanted to record a data set that had multiple interpretations of the state trajectory. And so to do that, I ran an ideal UGV model using the original bicycle model with no perturbations, and then a faulty UGV model with a random perturbation from the noise functions that I created. And then both of them were subject to follow the A-star path given, and then report back their trajectory data. And so in addition to that, I also recorded the velocity, the steering, and then the timestamp of each individual record. So I have this feature vector, which is in 1x12, and it is the three residual values, the three residual state values between the ideal UGV and the faulty UGV, the three raw coordinate data values, and then the three coordinate values of the error between the desired path and the actual achieved path of the faulty UGV. And then I ran the simulation 100 times per classification, which ended up giving me a data set which was in 276,000 by 12, so 276,000 samples of this feature vector. So one more thing before I actually get started training is I wanted to run a feature selection algorithm, because while the feature that I'm using is a relatively small feature, the difference in the number of input variables will drastically affect the runtime, and also it could possibly affect the accuracy, the total accuracy of the classification model, where possible irrelevant or redundant or noisy data features are still kept. So the first thing I did was I used PCA, principal component analysis. The idea with PCA is that you want to reduce the dimensionality of a data set by combining features into new components. The problem with this is that it's not getting rid of data, it is just re-representing them on a new basis. So in theory, it could possibly retain irrelevant or redundant noisy data. But the process of doing it is you have, in your original data set A, you compute a feature covariance matrix. So it's the covariance between each of the features in your data set. And then you compute the eigenvalues and the eigenvectors of your covariance matrix, and you store your eigenvectors in V. And the idea with this is your eigenvalues which are sorted from highest to lowest, will explain the most variance to the least variance in your data. And the idea is that you want to keep only so many eigenvalues, i.e. so many principal components, to where you explain a certain percentage of your data set, or you just want to, for example, in the GA objective surface, you want to keep, a certain number of components so you can reduce the data set to a certain manageable size. What this is used for a lot is actually transmitting large amounts of data and compressing it so that you can reconstruct it on the other end. So for example, they use this on the Hubble telescope a lot to transmit really, really low resolution compressed versions of images and then reconstruct them back on Earth. And the way that you do that is you take your eigenvector matrix V, and then it's in M by L, and I mean L is the number of components you choose to keep. And then you compute the dot product of V transpose and A transpose, and then you transpose that back, which basically will give you back this reduced data set D, which is in N by L. And then in order to reconstruct the data set, you basically do the same thing, but you do V dot D transpose and then transpose the result of that to get you back to your original dimensionality. The problem with this, however, is that depending on how many principal components you take out, you have an error between your original data set and your reconstructed data set. And so what I did to try to identify what the error would be was I iterated through from one principal component to the full 12 features, so the full 12 components, and then I would calculate the L2 norm between the original data set A and the reconstructed data set A tilde, and then plot the Euclidean norm here. And as you can see, basically unless you keep the first couple unless you only are getting rid of the first couple of principal components, you are going to exponentially start to lose information. And in addition to this, what I also wanted to see if this would work in practicality was I took the LSTM model that I proposed and I would train it for 15 epochs or 15 iterations. And I did the same thing. I would iterate from one principal component to 12 principal components, train it for 15 epochs, and then plot the training and testing accuracy, which you can see the training is in blue and the testing is in yellow. I would plot the final training and testing accuracies versus the number of principal components used. And as you can see, from the first two principal components onward to the rest of the data set, you see fairly similar results in training. Although obviously the optimal feature set is all 12 features. So in addition to this, what I wanted to do in an attempt to actually get rid of possibly noisy or corrupt data was I wanted to use a feature filtering technique. And so basically what that means is you're still trying to reduce the dimensionality of a data set, just like PCA, but instead of combining them into new components, you are only selecting the features that have the highest correlation to your target label. So you're getting rid of feature vectors wholesale. And so what this means is that you can remove possibly irrelevant or redundant features. It also will decrease your training time, as will PCA, but it also will reduce your chance of overfitting. And so what I did was the way that you do this is you compute this correlation vector, where you compute the correlation between feature 1 to feature 12 against your target label. And then the other thing that I did to get an idea of how the data was distributed was I computed pairwise correlations between each of the features and themselves, as well as the label. And then I plotted this feature correlation heat map here. And what you can see is the last column in the heat map is the actual correlation vector. And then if you were to sort this from most correlation to least correlation, you would have the vector that we're using to determine the optimal features. And so with that, I did the same experiment that I did with PCA, where I started with just taking the first highly correlated feature all the way to all 12 highly correlated features, and then I would train my proposed LSTM model for 15 epochs, and then plot the final training and testing accuracies versus the number of correlated features that I kept. And basically what you can see here is a much clearer distinction between the number of optimal features to keep and the rest of the features. Basically what you can see is that from 4 until 12, there is not really much significant difference. So in theory, your optimal feature vector would be the first 4 highest correlated features, which actually are the X residual, the Y residual, the theta error, and the steering angle. And so with that, I reduced the data set from 276,000 by 12 to 276,000 by 4. And then as a final test, I went ahead and I did the full, so in order to fully train the LSTM model, I trained it for 1,000 epochs. And what I tested was I trained for the full amount of epochs for the full feature set and the quote-unquote optimal feature set. The optimal feature set is in this right figure, and basically what I get is a training accuracy of 96.5% and a testing accuracy of 94.8%. Whereas with the full feature set, it's able to achieve a training accuracy of 99.5% and a testing accuracy of 97.5%. So obviously, the full feature set, while it doesn't show much growth, it doesn't show much difference when you're just plotting them from the first few epochs. Basically what this says is that with a reduced data set, you can hit this quote-unquote optimal accuracy at the same time as the full feature set with less features and in less time, but you won't learn as much from the data as if you had the full feature set. The other thing to keep note is that the full feature set took approximately 200 minutes to train for 1,000 epochs. And this is based on the fact that it takes the first few epochs roughly 3 seconds to train. So if you multiply that by 1,000, you end up getting roughly 200 minutes. The thing is, though, is that that's not necessarily true. That's not taking into account throttling. So when I was running these experiments, especially if I was training multiple models, which we'll talk about in a second, the throttling issue was a really big deal, and it basically would exponentially increase this runtime. So instead of it taking 3 hours for 1,000 epochs, it would take 5 or 6 hours. However, with the reduced feature set, which is only a third of the feature set, you get 4 times the runtime performance. So basically, what you can confer from this is that if optimal solutions is your utmost importance, then you should use your full feature set. However, if suboptimal solutions are okay and your main the main thing you're worried about is runtime, then reducing your feature set would also be probably the better way to go. So one of the other things that I wanted to do just to make sure and prove that deep learning was the necessary solution for this problem was to compare it versus more real-time machine learning algorithms, i.e. much less powerful machine learning algorithms. And so what I did was I took the reserved testing data set, and I used that to accumulate these 3 performance metrics, which are accuracy, precision, and recall. So accuracy is the total number of correct predictions out of your total data set. Precision is your false positive rate, and then recall is your false negative rate. And I did that for these 6 classifiers. So the proposed LSTM, quadratic discriminant analysis, linear discriminant analysis, k-nearest neighbors, logistic regression, and support vector machines. And as you can see, basically the only classifier that even gets remotely close is k-nearest neighbors, and it's still a significant performance difference from the LSTM. So just solely based off of performance metrics, classification performance metrics, the LSTM is clearly the way to go.